Hi, this is Brian and welcome to Homework 2 for Stat Inference. I'm going to work through the problems here and make sure you've tried them first and looked at the hints and looked at the answers and then watch this video. And again, I'm going to teach you how to create these kinds of slides in the data products class if you're doing the specialization. So the first problem is one of these basic conditional probability problems. It's sort of like a little bit of probability calisthenics just to warm us up. So what it asks, and this probably is better in homework 1, but I think it kind of crept into homework 2 as a legacy issue. So the probability that the manuscript gets accepted to a journal is 12%. However, given that a revision is asked for, the probability that it gets accepted is 90%. Is it possible that the probability that the manuscript has a revision asked for is 20%? Okay. Let me switch over to my handwritten notes and then we'll try and answer this. Let's let A be the event that the article is accepted and B be the event that a revision is asked for. And if I go back to my numbers, they gave me probability of A is 12%, and they gave me the probability of A given B, the probability of accepted given a revision is asked for, is 90%. And the question is asking, could it be that probability of B is 20%? Well, the probability of A intersect B is equal to the probability of A given B times the probability of B, which is 0.90, and we're hypothesizing that probability of B could be 0.20, which is 0.18. So can it be the case that A intersect B, this area, is 0.18, when we know that probability of A, this whole area right here, including the red area, is 0.12. Well, that's not possible because the red area is contained inside the green area, so it has to be smaller than 0.12. So this isn't possible. So let's try that out as an answer and see how it goes. No, it's not possible. And then submit and OK. And then if I click show answer, it'll actually just go through the work there. And then, by the way, you can always click on show hint and it gives you some basic, a basic starting point for the problem. Now the next problem is kind of important because it's getting us up to the point where we can work with standard normal calculations and non-standard normal calculations, which is sort of an important part of being a data scientist. These should be fairly natural things to work with for people. So it says, suppose the number of web hits to a particular site are approximately normally distributed with a mean of 100 hits per day and a standard deviation of 10 hits per day. What's the probability that a given day has fewer than 93 hits per day expressed as a percentage to the nearest percentage point? So let me switch over to my notes and I'm going to draw the relevant normal distribution. So here it is. It's 100 is the mean, and it wants to know what's the probability of 93 or fewer hits per day. So it wants that area. Well, we need to figure out how many standard deviations below the mean 93 is. So we do that by taking 93, subtracting 100, and dividing by the standard deviation, which is 10, which we get negative 0.7. So let's, so we don't know that standard normal quantile off the top of our head. So why don't we go to RStudio and type in pnorm negative 0.7. So if I type in pnorm negative 0.7, then I get 24%. I would also add that R can just do this calculation for you. You don't actually have to convert it to standard normal quantiles. So as an example, if I were to just type in pnorm 93, where the mean is 100 and the standard deviation is 10, it's going to give me the exact same answer. Probably the most common mistake you would make on this one is to accidentally do pnorm 0.7 by itself, which is 0.7 standard deviations above the mean and lower. So that would be this probability right there, so 107 and lower. Okay, so that's an important distinction. 24%, submit, and there we go. So this homework problem is a Bayes problem, and it corresponds pretty closely to an example quiz question. Now I've kind of marked some of the correspondence between the quiz questions and the homework problems in the quizzes, so look for that. And it says, suppose 5% of housing projects have issues with asbestos. The sensitivity of a test for asbestos is 93% and the specificity is 88%. What's the probability that a housing project has no asbestos given a negative test expressed as a percentage, blah, yada, yada, yada. So I've gone ahead and written out the information here. A is the event that the house has asbestos. D plus is the positive test. D minus is the negative test. And what I've been given is this marginal probability of a house having asbestos is 5%. The sensitivity of the test, which is the probability of a positive test given that the house has asbestos, is 93%. The specificity is the probability that the test is negative given that the house does not have asbestos, and that's 88%. And we want the probability that our house does not have asbestos given that we had a negative test. That's what we'll be interested in. Okay, so this is equal to the probability of A complement intersect D minus times, or divided by the probability of D minus, which is equal to the probability of D minus given A complement times the probability of A complement. And probability of D minus is equal to probability of D minus intersect A complement plus the probability of D minus intersect A. And now we can write, let me start over on this line. Let me rewrite the numerator. That's the probability of D minus given A complement, which is the specificity, times the probability of A complement, divided by the probability of D minus given A complement, which is the specificity again, times the probability of A complement, plus, now let me work with that guy, that's going to be the probability of D minus given A times the probability of A. So let's start plugging in our numbers. The specificity is 0.88. The probability of A is 0.05, so 1 minus that would give us the probability of A complement, so that's 0.95. Okay, and then this is just the numerator repeated again, so that's 0.88 times 0.95 plus, so this is the probability of D of a negative test given that the house has asbestos, and that's 1 minus the sensitivity. So remember, let me just point this little fact out. Let me use different letters too, just so we don't get confused. So let me say B given C. I want the probability of B given C plus the probability of B complement given C is equal to 1. And the way to think about this is when I condition on something like given C, then the probability just works like a normal probability as long as I have everything just conditioned on C. So probability of B plus probability of B complement equals 1, just because if I didn't condition on C, that would be true. And if I condition on C and keep C conditioned on in every probability, then all the same rules of probability apply. And that's an easy trick that you can use to calculate conditional probabilities so you don't get tripped up. Okay, so in other words, what we want probability D minus given A, but we have the complement probability D plus given A, but the condition on A is the same, so we can just 1 minus it, so that's 1 minus 0.93, so that's 0.07, times the probability of A, which is 0.05. And this works out to be about 100%. So I'm going to click on 100% and click submit, and then let me show you the answer where I actually plug it into R. So suppose that the number of web hits to a particular site are approximately normally distributed with a mean of 100 hits per day and a standard deviation of 10 hits per day. So the same numbers as earlier. And what number of web hits represents the number of days so that only 5% of the days have more web hits? Here's our normal distribution, 100. We want the point such that the area above it is 5%. Now, we could revert everything back to the standard normal, but again, we can just use R for these questions. So we want to do Q norm 0.95. Now that's a subtle point. Remember, Q norm is always specified in terms of the probability of the quantile and below. So just to remind ourselves, here we wanted the point here so that 5% lied above, but that would mean 95% lied below. Okay, so just remember that when you're dealing with Q norm. So we want Q norm 0.95, and if we hit return, it's going to give us the standard normal quantile that we remember, 1.64. So we know that that quantile is 1.64 standard deviations away from the mean. So we could, we could pretty easily just do that, right? 100 plus 1.644845, let's just give it the whole thing, times 10, so that's 116.44. That's the answer, but let's actually just do it how we would do it without doing that calculation. So we would want Q norm 0.95, and then we'd want to just tell it that the mean is 100 and the standard deviation is 10. And then you can see it gives the same number. Okay, so 116.4485, and it says give it to 3 decimal places. So that would be 116.449. 116.449, and I'm going to click submit, and there you go. I think the tolerance is actually a little bit more forgiving than what I specify in the question. Now here's another take on the same problem. So it says suppose that the number of web hits to a site is approximately normally distributed, mean of 100, standard deviation of 10. And it says imagine taking a random sample of 50 days, what's the number of web hits that would be the point so that only 5% of averages of 50 days of web traffic has more hits. So it's kind of like the same problem, only it's not talking about a random draw for this population, it's talking about a random average of 50 points from this population. So remember, our original population looks like this. It has a mean of 100 and its width is governed by the standard deviation of 10. But if we were to take samples of 50 over and over again from this distribution and take averages, they would themselves have a distribution that would also be normally distributed. And it would be centered at the same place, 100, but its standard deviation, instead of being 10, would be 10 over square root 50. So it's the same exact problem, only now instead of having a standard deviation 10, it's having a standard deviation 10 over square root 50. Let's try it. So now we want to do Q norm 0.95 with a mean equal to 100 and a standard deviation equal to 10 divided by square root 50. And that gives me 102.33. And so I'll copy that number. Notice it's much closer to 100 than 116, right? And that's because that normal distribution is much more concentrated about 100. There, I'm going to plug it in, and that's to plenty of decimal places, so it should work. And there we go. And then you can see the same. You can see the same exact code. So this is a p-value question, a binomial p-value question. So your friend claims that they can distinguish between cheap and good wines, and so you randomized a bunch of varieties. So you got a cheap Merlot and an expensive Merlot, and you gave them to your friend in random order, and then you got a cheap Chianti and an expensive Chianti, and you gave them in random order. And she got 5 right out of 6 varieties that you tried. And the question is, what's the chance, if she was just flipping a coin each time, what was the chance of getting 5 or more right? So 5 or 6, that would be the p-value. That would be the probability of getting as or more extreme evidence in favor of the alternative, assuming where the probability calculation is done, assuming that the null is true. All right, so let's just do that. So we want the binomial probability of 5 or 6, okay, if the coin were fair out of 6 trials. Okay, so we want p binom, we want 5 or 6, so I'm going to put 4 here, and I'll explain why in a second. I want size, the number of coin flips equal to 6, the prob is equal to 0.5, 0.5, and lower dot tail equals false. Sorry, working on a small keyboard here. There we go. So it's 11% if I round to the nearest integer percentage. The reason I do 4 is because by default, p binom will do 4 and lower. But then when I put lower dot tail equals false, it's going to do strictly greater than 4, so 5 or 6. Okay? So as an example, if I were to do 1 minus p binom where I omitted the lower dot tail, it's going to give me the same number, 11%. Okay? So if I do p binom 4, it's going to give me 4 or fewer, and if I do p binom 4 with lower dot tail equals false, it's going to give me strictly larger than 4, which is 5 and 6. So the two p binom 4 without the lower tail and p binom 4 plus the lower tail have to add up to 1. So I'm going to go here and plug in 11%. And then I'm going to click show answer, and it's going to show it. I round it to, I guess, an extra decimal place there to give 10.9. Okay, now let's do this question, which is a central limit theorem question. Consider a uniform distribution. If we were to take 100 draws from a uniform distribution, which has mean 0.5 and variance 1/12, so I give you that, and I take their mean, x bar, what's the probability of getting an x bar as large as 0.51 or larger, expressed to 3 decimal places? So we don't know much about the means of uniform distributions exactly, but we do know that they should be approximately normally distributed. So let me switch over to R, and we'll just try and do it. So recall that my mean was equal to 0.5, and my S, my standard deviation, or my sigma, let's say, was equal to square root 1 divided by 12, and then divided by square root 100, which is 10. Okay, so sigma is about 0.03. So we want, that's the distribution of the sample average of 100 uniforms. It has the same mean as the original uniform distribution, but its variance is squashed down a lot by a factor of, a factor of 100, and its standard deviation is shrunken by a factor of 10. Okay, so I want p norm, I want 0.51 with a mean of equal to this mean that I set, and my standard deviation equal to the sigma that I just set, and I want lower dot tail equal to false. And that gives me about 36%. And I'm just going to copy the whole number so I get all the decimal places. And I submit. And let me show the answer just to make sure we agree. And it's the same calculation. I would note there was a little bit of a poor programming I showed in there. I overwrote the default R function mean with a variable called mean, and that's a bad programming practice. So, you know, I'm actually a little glad I did that so I could point this out. If you need to check whether R has a function predefined, so let me remove my mean variable. Now if I type in mean, you can see that it's already defined as a variable. So don't overwrite basic R functions. That'll mess up your program pretty easily. Okay, good. One that I can just do. If you roll a standard die, and if you roll 10 standard dice and take their average and repeat this over and over again and construct a histogram, what would it be centered at? So what would the average of 10 dice be centered at? Well, the average of single die rolls is, if I were to roll a die over and over again and just get the sort of uniform distribution that it looks like on the numbers 1 to 6, that histogram would be centered at 3.5. But I know that the average of 10 dice has to be centered at the same thing because the distribution of averages is centered at the same place as the original population. And so it has to also be centered at 3.5. Great. Now, it wouldn't be the same distribution, right? Because it's averages of 10 dice, not a histogram of die rolls, it would be more peaked around 3.5, which is basically illustrating that taking average is a good thing. It reduces variation in the distribution. Again, here's another similar problem. If I roll 10 standard dice, and I take their average and repeat this over and over again, and construct a histogram, what would the sort of variance of those distribution of 10 dice look like? Well, again, this is just asking what is the variance of the distribution of averages of 10 die rolls. And we know that it gets divided by 10, right? The variance scales down by n, the standard deviation scales down by square root n. Okay, and we also did a homework problem where we calculated what the variance of die rolls was, and it was about 2.92. And if you just go back in the notes, you'll see that we did that. So I know that if the variance of the distribution of die rolls, the uniform distribution on the numbers 1 to 6, is 2.92, then the variance of the distribution of averages of 10 die rolls would have to be 2.92 divided by 10. So that's 0.292. I'm just going to go ahead and put that in without doing any R or anything, and I'm going to submit it, and you can see the answer. Here, when I show the actual calculation, you can see that I calculate the variance of a die roll. And that's just reiterating the calculation done in class. But the important thing here is to remember that we're dividing this variance by 10. So the number of web hits to a site is Poisson with mean 16.5 per day. What's the probability of getting 20 or fewer in 2 days expressed as a percentage to one decimal place? So we want 20 or fewer hits where we know that the rate of hits is 16.5 per day. Okay. So the Poisson probability function is PPOIS. There you go. And we want 20. And the lambda is 33, 16.5 times 2. So what I mean by that is we don't want the number, we want 20 hits in 2 days. We want the probability of getting 20 hits or fewer in 2 days, not for 1 day. And so if the rate is 16.5 per day, then the rate is 33 per 2 days, okay? And so when you do that, you get about 1%. So I want to go here, and I want to plug in 1%. Oh, don't include the percent sign, and submit. And then let me just show the answer. There you go, right there. I actually do the rounding in the R command there, so you can see that it's multiplying it times 100 and rounding it to one decimal place. But that's all that question was asking you to do. But let me just comment really quickly. Remember, the Poisson distribution is a distribution on counts, and it depends on this rate parameter, lambda, that has time units or units of whatever is being measured. So in this case, if we say something is Poisson with rate 16.5 per day, and we want to talk about Poisson probabilities of 10 days or 100 days or whatever, we need to multiply that lambda by the number of days we're considering. So that's the only little bit of treachery in this problem, and you just have to keep track of that. So that's the end of this homework. You've earned yourself a treat. I'll post another video for homework 3 and homework 4 in a couple of days after that.